So probably not everyone knows what this Chvátal-Gomory rank business is, so let me just first start by defining it. The setup is you're given a polytope P, and you actually don't really care about the polytope P. The real polytope you care about is the integer hull of P, so that's the convex hull of the integer points, those blue points. So you want some kind of procedure to get you closer to this integer hull, right? So one way you can do this are what are called CG cuts. So let me just define that by example. So let's look at this purple inequality, right? So if we imagine that bottom left point as the origin, that purple inequality is just x plus y is at least 2 plus epsilon. And the nice thing about that inequality is that the coefficients that appear on the left-hand side are all integer, right? So when I substitute in one of those blue integer points, I'll actually get an integer, right? So that means that I can round that 2 plus epsilon up to 3, right? So I get a stronger inequality that's valid for the integer hull. Okay, that's a CG cut. Here's another CG cut. Again, this inequality has integer coefficient on the left-hand side, so I can round to get a stronger inequality, that guy, right? So if you take all the inequalities that you can generate in this way, you get this rectangle, which is called the CG closure of your polytope. Okay, so this is just the formal definition. You don't have to read it. So the CG closure is just the possibly smaller polytope you get just by rounding inequalities, right? And you can iterate this procedure. So you can take the closure of the closure, and that allows you to define the teeth CG closure. And so now the smallest t such that the teeth closure is equal to the integer hull, that's what we'll call the CG rank of your polytope, okay? Now, it's unclear that this number is actually finite, but Chvátal proved that, in fact, this procedure will terminate after a finite number of rounds for every polytope. Okay, so the question that I want to talk about in this talk is when is the CG rank of a polytope in the n cube bounded by a constant, right? So if I tell you that the CG rank is at most 100, can you say something about what the polytope looks like? And this question is sort of more conveniently phrased in terms of reverse CG rank, right? So reverse CG rank is where you start with a set of 0, 1 points S, right? And then you look at all polytopes R contained in the n cube whose set of 0, 1 points is exactly S, okay? And then you take the worst one, right? So you take the largest CG rank among all those polytopes, and we'll call that the reverse CG rank of S, okay? And so the characterization that I have in mind will be graph theoretical. So let me tell you a graph, right? So it's convenient to look at the vertices that are not in S, S bar. And you can think of those vertices as a graph, right? So those are actually vertices of the hypercube. So you can just take the induced subgraph of the hypercube. And so now the question is, let's call that the forbidden graph. Right, so if the forbidden graph has a simple structure, does that tell you that the reverse CG rank is small, right? So a priori, it's unclear that it should, right? This is just some random graph that I thought about. But it's true for, say, the simplest graph that you can think of, right? So if the forbidden graph is a stable set, then the reverse CG rank is at most 1. And so our work is inspired by a nice paper of Cornejos and Lee from last year. So they prove that if the forbidden graph is a forest, then the reverse CG rank is at most 3. And if the forbidden graph has tree width at most 2, then the reverse CG rank is at most 4, right? So those are exactly the graphs of tree width at most 2. So you might wonder whether the reverse CG rank is bounded as a function of the tree width of the forbidden graph. And that turns out to be true. So we proved that for all values of tree width. And we were kind of lucky in doing that. So we were lucky in the sense that actually tree width is not really the right parameter to think about. And once you sort of know the right parameters, everything becomes easy. Okay, so let me tell you what the right parameters to think about are. So the first one is what we call pitch, right? So the pitch is the smallest p such that every p-dimensional face of the cube meets some vertex in S, right? And it turns out that if your set has large pitch, then the reverse CG rank is also large. So if you want a theorem, you definitely need to bound the pitch, okay? And the second parameter is what we call the gap, right? So the gap, again, you don't really have to read that, but the gap is just a measure of the size of the facet coefficients you need to describe the convex hull of S, right? And again, if the gap is big, then that implies the reverse CG rank is also big. So again, if you want a theorem, you also need to bound the gap, right? And it turns out that that's all you need to bound, right? So if you've got pitch P and gap delta, then your reverse CG rank is also bounded, and the bounding function is very reasonable, right? So, and as a corollary, we get the tree width result that I alluded to earlier. In fact, we get something stronger, right? So it turns out that you don't actually have to bound the tree width. You just have to forbid subdivisions of big cliques. And once you do that, it turns out that you automatically bound the pitch and the gap. So if you just plug those into our main theorem, you get that bound there. So that's it. Thanks.
Thank you. Any questions?
Can you state the pitch or gap in terms of this graph theoretic thing you're talking about, and like the graph with the S?
Yeah, so I guess the gap is not really that nice because that's really more of a function of that point set. But yeah, like the pitch is just essentially the largest, like, well, it would be the largest p-1 dimensional subcube that you have in there, right? So, and you would want to forbid something like that because if you've got a large subcube in this forbidden graph, your problem is kind of very complicated.
What about lower bounds? I mean, how close is C plus P minus 1?
I don't know. Like we tried a bit. Like there's a paper by Eisenbrad and Schultz that says that the CG rank is, well, it's at most like n squared log n, but there's a lower bound of n squared as well. But it's hard to kind of improve either one of those.